Thanks, Kirill, for the nice introduction, and welcome everyone to my talk on modeling. And with modeling, we always mean, like, we have in mind some optimization of traveling wave parametric amplifiers. Yeah, that's the outline. So quick shot on where we are in our quantum ecosystem. Then I want to just bring you closer to the model of what are the ingredients of the quantum model that we are establishing in order to optimize these systems. Then we actually look at some optimizations and then some outlook, basically, going beyond the approximations that are in the modeling. Okay, so where are we? So we try to contribute and to kind of improve superconducting quantum computing. So think of this cartoon here of a dilutional refrigerator. The device we are considering is here at the readout part. So I tried to sketch here a typical qubit readout scheme. And this basically looks the following. At room temperature, you typically have like a signal source, maybe a vector network analyzer, whatever. You drive a pulse, a probe pulse, a readout pulse, drive it down here to the very lowest temperature stage where your QPU resides. It's like basically a qubit that loads a resonator. And what you get is a dispersive shift for the pulse that propagates along here. And here we are talking about signal levels in the range of tens of microwave photons. So like ultra low power signal, not to interfere with the state of the qubit. And now you want to classically, at room temperature, detect that signal. Again, and you want to do a discrimination whether I have a qubit 0 state or a qubit 1 state. So you want to actually do the readout. So of course you need to amplify. You're doing that typically with transistor-based high electromobility transistor amplifiers, but to get like really, really good readout fidelities, you want something in the millikelvin regime down here, where we couldn't put the amps because they have too much dissipated power. So what we are interested in finally are the traveling wave parametric amplifiers. Now that's actually typically also the range for JPAs. JPAs are used often here, but we want to have them broadband such that we can like read out multiple qubits at once. This is the main idea. There are some physical realizations here, but let's look on what are the actual ingredients. What do I need to construct such a traveling wave parametric amplifier? So this, in principle, what is like everything what that is in our model. So we can construct a circuit view of such a system, so very simplistic circuit model, and construct a unit cell model of a transmission line. So here you have a 50 ohm transmission line, here you have a 50 ohm transmission line. In the center, you also want to have it matched to 50 ohms such that you don't get any reflections, because any reflection basically kills you. You have just 10 photons propagating in. You want to amplify these photons, and you don't want anything back at your qubit. That's the idea. So what do you do? Well, here I already kind of put it. You also need a pump, because what you want to do is you want to nonlinear interact with your signal with a pump mode. So you want to send in a strong pump tone, you want to destroy some pump photons and bring this energy back into your signal photons to amplify them coherently, such that you can detect them. So, and you need some nonlinear device to do that. And in the superconducting regime, this nonlinear device is given by some Josephson junctions. So you periodically load your transmission line with Josephson junctions. The problem here is, of course, like, in theory, this is all nice and easy. In reality, there are quite some restrictions on these junctions. They all need to be similar, they all need to be same, and you want to parameter target them such that also here you get some impedance matching and still have a 50 ohm transmission line in the center here. Additionally, you have some ground capacitance due to the coplanar planar structure. The junctions themselves have some Josephson capacitance because they kind of build a plate capacitor. And we have a lossy substrate. So we have a lossy microwave substrate, some silicon dioxide, whatsoever. So also these losses should, in a good model, be included in order to match experiments realistically. So now we can construct our model. And yeah, well, this is like a circuit theoretic model, but the theory we are kind of working in is quantum circuit electrodynamics. We need a quantum theory of the energy that propagates, like of the electromagnetic modes that propagate through that structure, because in the end, what is interesting, what are the interesting metrics of an amplifier? We want to know, first of all, what's the gain of the amplifier, so how much does it amplify? But a very, very critical thing is the noise the amplifier adds. So we really want to quantify how much noise is there. And these amplifiers are actually quantum-limited devices. So we need a quantum theory to quantify this noise. So the idea here is, okay, we have our unit cell structure, and out of this unit cell structure, we construct a Hamiltonian. So we bring in our nonlinear part, we do some Taylor approximation, so some tailoring, some expansion, have a linear part of that, have some full-wave mixing part of that, so like the second part, get something that corresponds to this Josephson capacitance, something that corresponds to the ground capacitance. In addition, we can also bring in substrate losses and the associated fluctuations due to dissipation fluctuation theorem by coupling this whole Hamiltonian to a heat bath that models the lossy substrate, basically. That's also in our theory. As a quantization variable, we use the flux, or the quantum phase difference, across the Josephson junctions, and then we kind of decompose it into individual modes, get some mode creation and annihilation operators, and construct our quantum theory out of that. So, after pages of calculations, and if I say pages, I mean really like hand-sketched pages of derivations and calculations, we finally arrived at some rather simple coupled mode equations for the signal mode and the idler mode operators, which we can solve analytically if we do some approximations. And the approximations we are doing is, first of all, the stiff pump approximation. So we assume that, and this actually violates energy conservation, so that's quite of a stretch, I would say, but it allows us to get analytic solutions. So what we assume is that the signal is so small that it actually does not really dissipate a lot of energy out of our pump mode. So the pump mode doesn't see, so if I create a signal mode, I don't do nothing with the pump mode. The pump mode still remains constant, basically. So we have this thing, we couple in losses, so we have some loss terms in, we couple in the associated fluctuations for the noise, and we can run this, we can get analytic solutions, and compare how we perform against experimental data. And this is what comes out. So if we look at experiment here, the gray curve in the background for the gain, and the prediction we get from our theory for the parameters in this paper from the VTT group, we see, well, hey, this matches really nicely. So we can actually be predictive. We can actually kind of, and we, in our theory, basically just used all the parameters that they have given in their paper. So it's like basically there is a table in the appendix. We just use the tabularized parameters, run it through our model, and this is what we get. The cool and new thing for this theory is also we get the added noise in the system. So this is the blue curve in here. And also this, they characterized here the noise temperature within their amplifiers. Also this matches perfectly, actually, within their experimental uncertainty. And that's actually a cool thing for us. So we were quite happy about this result. So this means we can model traveling wave parametric amplifiers analytically to some extent, quite well, get nice matching to experiment. Now, why do we want this model? Because not we want to remodel something from the experiment, we actually want to be predictive. We want to engineer new devices. That's the idea. So the natural question is, can we do any better than that? So what are the options that we have? We could say, well, let's just stick with the theory that we have so far, or with the topology that we have so far. We have a transmission line and we periodically embed single Josephson junctions in there. Well, we can do that. Then we can come up with some ideas. We can do some dispersion engineering, bring in some additional resonators to match the signal and pump mode velocities through there, fix this phase mismatch, increase some gain bandwidth by some other techniques, decrease the added noise, so reduce substrate losses, do whatever, make some clever choices. Can we do any better? Yes, we can. Or we can go a different route. We change the topology. So we find a more optimal topology. We add some degrees of freedom in our junction design to increase the nonlinear interaction strength, get more gain out of the system at less noise. This is the main idea. So those are the possibilities that we have. And we went along both routes. So this is one route where we included some resonant phase matchers in our model. We could also quite nicely, the gray results, literature results, it's a pure theory paper, which we also nicely kind of reproduced. The theory in the other paper didn't take into account losses. Therefore, there's this kind of slope shift here that we have. We also take into account losses, but our model really performs well also under the assumption of these resonant phase matching topologies inside of these structures. Then, the other way we can optimize the structure is, well, let's change the topology. Let's start off with something new. So let's still have a transmission line and periodically embed some nonlinear elements, right? But instead of single junctions, we keep it open. We don't really specify what this nonlinear element may be. I mean, in superconducting transmission lines, this will always be some arrangement of Josephson junctions, but we let it open for the moment. We still consider losses, we still have some ground capacitances because we have a coplanar transmission line structure, but we probably also allow for the system to be flux pumped, so to be externally modulated by an additional linear transmission line that flux couples with our Josephson nonlinear elements, right? So this is our next approach, how to optimize the structure, so give ourselves a few more degrees of freedom. So let's now closer investigate what's going on in here, right? So the most general thing you could do is you could treat this here really as a black box. I have no clue what it does. I just know it has some nonlinear response. So the current somehow will depend nonlinearly on the phase that's across the junction. So what I can do is I can blindly do a Taylor expansion and say I'll have some coefficients that will have some linear response and some 3-wave mixing or 4-wave mixing nonlinear responses. And as candidates for this Josephson nonlinearity, we can browse the literature, we can look it up, we can say we have some single junctions, as we've already demonstrated. We could have some RF squids, DC squids, or snails, for example, which are different arrangements of junctions, as we can see here. So an RF squid, DC squid, snail, they all are loop-like structures, so we have additional degrees of freedom. We could drive them with an external bias field, drive them into different operation points. So we added a degree of freedom that we can use for further optimization. Because by adding this external flux field, so in all the describing current phase relations that we get, we have some dependence on this external flux field, this phi b, and by that can tune how the devices operate, and we can then tune, in turn, these parameters C2, C3, and C4. So that's the idea we have. An additional possibility is then even going one step further and making this bias field time-dependent. So we don't use just a constant field, we use a constant field to driving it to some operation point, but in addition we use a coupled second microwave line here to introduce some smaller fluctuations around that, to do a time-dependent modulation of the system, and this is called the flux-driven traveling wave parametric amplifiers, given this theory paper by Zorin here. This was the idea. And we included that as well in our theory, and there the main idea is, well, we don't use the intrinsic Josephson nonlinearity for wave mixing, but we use this nonlinear modulation of the linear part of the system, and then do basically here a second Taylor expansion around this flux-driven point, around this DC bias point. That's the idea. And with that, we have now several options in how we can operate these new devices. So we can make a table, tabularize, and see what's the best topology for us, right? So what we do is we look at this and do a directly pumped RF squid, DC squid, snail, and a flux-driven RF squid, DC squid, and snail. And just look at the parameter range that we have. Look at what can we optimize and how can we, let's choose the best structure out of that. So we just run simulations with the parameters, or we just calculate these parameters analytically, basically. So let's say we want to have a tupa that operates in 3-wave mixing. So what we want is we want the C3 constant, or the coefficient, the 3-wave mixing coefficient, maximized while we have 0 4-wave mixing, 0 cross-phase modulation, additional modulation products. We want to zero them out. So we want to operate at a point where the C4 coefficient is actually 0. And if we do that and browse all these different structures, we see, well, the flux-driven RF squid is the best. This should be the worst. It's 0 everywhere. Regarding these kind of optimization targets. But is this really the case? Is this the truth? And it turns out it's not. Because what we actually need to do is we need to really look into the Hamiltonian, how the Hamiltonian is then formed, and keep everything still black box. So we don't assume any inductances, we don't assume anything. It's just all written down in these coefficients C3, C2, C4, right? And if we do that, we notice that in front of our 4-wave mixing term, or 3-wave mixing term here, this is the 3-wave mixing, we annihilate a pump photon, this is treated as a classical mode, create a signal and an idler photon here. In here, we have the coefficient C3, but it's scaled by the coefficient C2 squared. So it's scaled by the linear inductance squared. So this enters way stronger than the actual C3. So we need to take this into account and optimize for this global coefficient and not just the 3-wave mixing coefficient C3. That's very important. So what we also need to take into account is for all these devices, we need to take into account the inverse linear inductance, the C2 coefficient. And if we look at that, we want to have this as small as possible because here it enters squared in the denominator. Right? And if we do that, then we actually find that the best device is the snail. According to these metrics, if we want to have a 3-wave mixing thing, the flux-driven snail is the most promising device according to these metrics. Well, we can take a snail. A snail consists of a small junction and a number of large junctions. We used 3 in this case. And what we did is we plotted our degrees of freedom. What choices do we have? Well, we can choose how small we make this snail in comparison to the big, like the small junction in comparison to the big junctions. And we can also choose the DC flux bias that penetrates this loop here, right? Those are our degrees of freedom. So this is our design space that we basically have. So we evaluate this design space and then again, go along with our design goal. We want to have 0 for cross-phase modulation, so the 4-wave mixing coefficient should be equal to 0, the C4 coefficient. And if we look at this plot here, this is true on this along this red line here. Then we use this red line, translate it to the gain plot, and choose a point where the gain gets maximized. That is the idea on how we optimize our trailing wave parametric amplifiers for maximum 3-wave mixing with 0, ideally 0 residual 4-wave mixing, right? If we do that, we can take these parameters and run it through our quantum model, the same model I've described previously. Now we just kind of supercharged it and made it this black box thing. We really just plug in the individual C2, C3, C4 parameters and not hard code the single junction architecture in as we had it before. And if we do that, we can make basically the same predictions. This time we get a large gain, nice bandwidth, very low added noise, very close to the quantum limit. So this is actually a cool thing. And we're actually working together with Kirill and his group, with Daniel, who's probably also in the room. No, he isn't. To get this really then done. But it turns out to be rather difficult, actually. So this is the device that Daniel manufactured at the WMI. It's actually according to these parameters that we optimized. It's the 0.12 alpha point, so it's a point somewhere here. It's not at this point because we chose it to be more stable to variations in the phi b, so if you don't have a perfectly homogeneous field. But still, it's rather difficult. So we notice a lot of problems in the experimental realizations, and the next steps are basically, together with Kirill, together with Daniel, get a better understanding on how we can actually improve the device and do some careful process modeling, have good control over the lab facilities, and get better parameter targeting. And what we rather recently kind of discovered is that we also need some very good phase velocity control in the pump line and in the nonlinear tuba line. So because if we get bad phase matching in these two lines, your amplification is going to shit. So this is also something we need to control better. In theory, this is a parameter we easily set. In experiment, you need to find ways on how to actually implement that and do that. So yeah, that's ongoing work. Okay, then if we kind of outperform this device, we go like very into the regime where we get like maximum gain. Our theory predicts kind of the holy grail tuba, 60 dB, bandwidth of 8 gigahertz, kind of the holy grail device. However, again, back to what I said previously, I wouldn't trust these results. I wouldn't trust my own model because we had these approximations and we had the stiff pump approximation. And for a gain that is this large, even if you say have just like a bunch of microwave photons at the input, it gets amplified down the line, and at some point the stiff pump approximation becomes invalid. It still assumes it. So what we need is, we need some ways to go beyond the stiff pump approximation for further optimizations. And this is where we now actively work on. And we came up with some interesting approach that I want to share, which also very well connects with some previous talks on some symbolic numeric co-simulation. Because, what do we want to do in the end? So as soon as we get to higher pump power, so we pump it even harder, we want to try to get more signal out, high gain amplifiers. What becomes more and more of an issue is we get more and more modes populated, more and more side modes populated. So this nice clean coupled mode equation theory that we have is not a good approximation anymore. So we get more and more side modes populated, which we need to consider in our quantum model. And anybody who's doing like bosonic quantum models can probably confirm that the more modes you have, the more nastier things get. So this is a bad thing. But it's particularly important to provide some nonlinearity measures of the amplifiers. See, for example, the 1 dB compression point. And basically just go beyond the stiff pump approximation to make things better matching with reality, with experiment. So this is the idea. And what could also be interesting, of course, is the quantum features of the light or of the microwave energy that leaves the tuba. So how entangled are these photons? Is there some cool statistics that we can observe? For example, using some G2 measurements. Can we predict this? Well, if we want to do that, we would need some fourth order correlations and second order correlations at the output of the output field operators of our tubas. So we need to calculate that. And now we need to do this for more and more and more and more modes. We can do a systematic approach for that. So what we can do is we can just write the first order moments into some order operator. We can do the second order moments, third order moments, and so on and so forth. And give ourselves a strategy such that we don't double treat variables. We always keep daggers to the left, so we introduce some normal operator ordering, right? So we do some bookkeeping of the variables in our system and write them into some ordered systems. And then we can write some pretty simple evolution equations. We say the ith order, the time evolution of the ith order is given by some huge matrix. That depends on all orders j, where j can in principle run from 1 to infinity. And we have some incoherent terms as well, some losses, some baths, whatever is in our model. Of course, to really treat this on a computer, we need to introduce a truncation scheme. So we need, at some point, we can't go to infinite order. At some point, we need to truncate and say the kth order only depends on moments of k minus 1. So this is some scheme we need to introduce just to make it finite and solvable, right? Okay, we can do that. And then we can look at the computational demand of this thing. So just naively solving this equation. If you do that, you will notice that, well, if I want to go to fourth order to kind of see some quantum features, and I just go to something like 10 modes in this naive picture, I will already consume some 43.5 gigabytes of memory. Still solvable on computers. In the previous talk, we heard something about 24 modes. If we are here, this easily becomes quite excessive, right? If we go to fourth order. But we have one advantage. And this advantage is that these matrices here, they're typically very sparse. And we want to make use of this sparsity by some additional analytic computations, some symbolic computations typically done on pen and paper to derive the actual minimum set of equations that you need to solve. But this can be huge if you get to 100 modes or so, or even 20 modes is huge. So derivation, you pile up paper. So what we want to do is we want to automatize this task. We want to get some symbolic computation framework that does the work for us. We want to teach a computer to derive the equations we want to solve, and then we want to automatically feed them to a numerical solver such that we get some results. And therefore, we browsed what symbolic libraries are available. There is, of course, Mathematica, everyone knows. There's some numerical quantum libraries out there. And there is SymPy. SymPy is kind of the standard Python symbolic toolbox. Who of you uses SymPy? Quite some, right? So you're familiar with SymPy? SymPy actually has a physics second quant module where you can derive like bosonic operators, bosonic creation and annihilation operators. You can load them, and then we want to basically do the steps that we just like outlined previously. We want to do some normal operator ordering to do our bookkeeping, and already there, SymPy struggles. Because if you want to do some normal operator ordering, apply a dagger. We want to bring daggers to the left. Your Python returns a not implemented error. Because it's only implemented for fermionic operators, not for bosonic operators. What we did recently, and which took us quite a lot of time, is we actually implemented it. So now, if you run, so we implement it in SymPy in the main library. We want to contribute this to the main project, to the open source project, such that all of you can use it. We just at the moment struggle with all the documentation work that's needed to kind of reflect it back into the actual GitHub project of SymPy. But we actually implemented it. If you now run Wix of AI dagger, you get the correct operator ordering. And this helps us in now doing some automated derivations and running them. And if we do that, we compare this now to our analytic solutions. If we still use the stiff pump approximation, we also compare it to some finite element time domain simulations. We have a code with this, a purely classical code, and we just compare the gain calculations and see, well, actually, this symbolic numeric approach really performs nicely. It performs quite well. We get actually the same results as from our analytic and numeric solutions. So this kind of confirms that's a cool way to go. We just need to focus on that and make this more versatile and kind of make this an integrated solution such that we can use it, and it should be open source such that also you can use it. And with that, I want to conclude. So what have we done? I tried to convince you that we got a quite nice model for traveling wave parametric amplifiers, which fits very well to experimental data. We used it for optimization, found out that snail-based flux-driven tupers are actually quite cool candidates, but hard to manufacture. And we presented our symbolic numeric approach to go even beyond that in terms of modeling, to go to many modes, go to beyond the stiff pump approximation, and get some realistic models in there. So next steps, overcome our experimental challenges, get some full spectral modeling, so especially also including pump leakage, and we want to also investigate the quantum features in the output signal of our tupa. That's the goals we have with our modeling, and in the near future, also together with Kirill. And yeah, I'm looking forward to some questions. Thank you.
Thank you, Michael. The talk is open for a couple of quick questions.
Hi, thanks. I've also heard about kinetic inductance parametric amplifiers,
Yes.
and they may be easier to fabricate.
They're typically easier to fabricate, but they're way larger. So they're typically like...
Okay. Have you looked into those as well? Or?
In principle, you can model them with the same model. There are some details that are different, but I mean, with the black box model, what you typically can do is like a kinetic inductance amplifier would just have a nonlinear kinetic inductance along this line, in principle. And you can just, in your model, replace that, like replace the Josephson nonlinearity with the kinetic inductance nonlinearity, and just run through the same thing. So we could, in principle, do that. We have not really done it because we're more interested in the tupa part. But in principle, it's possible, yes. And it's not even that different in terms of the model.
Thanks.
Right.
One extra short question, maybe? Maybe then I can ask my own question, because Michael, I was wondering whether the same semi-analytical approach can be used for other applications, for example, for modeling of cat states in the cavities, you know, with continuous variable quantum computation. Could one, in principle, envision applying this model for this direction?
You mean cat states as an input to the system, or cat states like as a state preparation system?
Rather as the second, as a state preparation, evolution.
So in principle, yes. So what we have here is basically the full operator description. So we have a Heisenberg picture description of the quantum operator that describes the box that we draw around here. So we put in a state as an input. Then we have a time evolution, the time evolution of an operator. We apply this operator, and then we get the state at the output. So in principle, yes, we can do that if we provide the right input. the operator is basically determined by the geometry, by the nonlinearities in the system, but we can get the output state then, really the state description. So yes, the model could in principle be used for that, I would say.
Okay, thanks a lot. Then in the interest of time, we have to continue. Let's thank Michael once again for his beautiful overview.